It was muted. Sorry about that. Okay. Is it? Can you guys hear me? Oh, okay. Yeah, the screen is this computer because of how IT is set up. Awesome. I cannot connect HDMI directly to the projector, which is kind of odd. Welcome back, guys. We are, oh my God. So we were talking about application layer where we talk protocol, the rule on how to send a message, the meaning of the message, and basically the syntax itself, which you can think of it as a grammar in normal language where we have to communicate between two people, right? In this case, we want two computers to communicate so we can establish the rule. Because when you design a computer, easiest thing you can do, imitate what human did. Think of human as a computer, how do they talk? Well, we build a rule on their language. Then we build a rule on how to communicate. Then we build an etiquette on, hey, don't talk at the same time, and things like that. And then let's redesign the language so that it's super efficient. All right. Then when the application builds that and pack the data it wants to send, right? From the application layer, you have the socket open. And you say read or write. It means that the client or the server will magically got the packet. Now let's zoom a little bit deeper into that magic because the sending process, right? You have to shove the message out the door, right? It had to rely on some form of transport infrastructure on the other side of the door to deliver the packet, basically, right? So there are two sockets involved, one on each side. And then on the more physical side of things, you have the internet that connect by a bunch of links, which connect physically each machine, right? Each machine are actually physically connected. If you think about it, there's once you connect to the Wi-Fi, that router is connected to ISP, the ISP connect to the world. And somehow we built this, we engineer this magic of connecting every ISP together among many other servers so they can talk to each other. All right. So that's a supporting layer. And in terms of the web service, basically this is where we will focus on today. We are not going to go into more of the communication side of things. We are not going to talk about how the network is built. We will talk about how to build a web service application. All right. The basic is we can use the, as you said, HTTP, which is a protocol. It's called hypertext transfer protocol. The client and the server will establish TCP connection. Anyone heard about this TCP connection? You might have seen it. How many people have seen that when you configure your computer? All right, you've seen that. You've also seen UDP, right? It's like most of the time you have this two types of connection, TCP or UDP. One of the key differences is TCP is a little bit more reliable, a little bit slower, sometimes a lot depending on how you configure that and how you build your network. The good side of this is things to happen in order. Basically, if you want to send a packet, the other side is guaranteed that you get the same order back, right? So that's also why it's a little bit slower because you have to make sure your packet is correct and in order. Yes. Yeah. And in this case, you have the client and the server connected through the TCP. All right. And TCP operate using just stream, something we know and love so far, which work on file, right? So that means kind of work with the socket model we have earlier, right? And then now that we have the two things connected, the HTTP govern how do I packet the information from one side to another. And there are multiple versions of HTTP. We'll talk about version 1.0, then 1.1, then version 2. All right. And there's also the coming of version 3, which by the way is different from Web 3. That thing is, in my opinion, is kind of bullshit. We can talk about it after class, but right now it's different from HTTP 3. All right. Okay, so for the web content, the web server returns the content to the client. The client is who? When you use Chrome, your computer becomes the client that connects to the server or whatever web page you want to open up, right? Let's say you want to book a flight somewhere, you want to travel, you want to exit from reality, from like just having to just took the exam. What website do you go to? Actually, what website do you guys go to when you book a flight ticket? Huh? Oh, you go to like airline website? Traveloka, okay. That works too. So for me, I use like Google Flight, like flight.google.com works pretty well for most like international flights. So go there, they'll procure first. What's the first thing you see? The text with some option to say, hey, what's the from and to, right? You want to fly from here to here, that you can put in afterwards. Then you can pick the date that you want to depart and the date of your return, right? So those are produced by whom? Who generate those things? The airline website, right? The server generate those options you can put in, send it back to your client. Then you put in whatever information you have, right? And you say search. When you do that, you send the data again back to the server and say, hey, this is my flight information that I would like to have. The server took it, processed it, hopefully search the World Wide Web of flight database to potentially list out these are flights you can buy, right? And then what do they send back to you? Flight information with the cost, right? Back to your Chrome client to display all the flights you can buy, right? So the content, when you actually transfer the data back and forth, these sequence of bytes are associated with what we call MIME or multi-purpose internet mail extension type. Some of these are things you've seen before, and you think about, hey, maybe there's a language, HTML, right? This is what you use to build a website. The HTML document, right, is a document that describes how a browser should display the information. Then you can put text / plain, which is unformatted text, image, GIF, PNG, right, in whatever format. And there are a complete list of these MIME types that the client, like Google Chrome, should be able to understand. Available at this link. You can check it out. But essentially, it's a different type of media. The media can be text, image, or audio, and things like that, right? These are that's why we call it media. All right. So that's the content, the web content. And it can be static or dynamic, right? A static content are things like HTML file, image, or audio clip, right? One of the good example of that is like the web portal at Mahidol University. If you go there for the main website, most of these are static content because I mean, you need to change that all the time while you're like using the website, right? So it makes sense to have a static content for these things. Then you have the dynamic content where you produce the content on the fly in response to your HTTP request, right? When you search for the flight, that better be dynamic because each connection is different. Each time, I mean, even from the same machine, right? You can go to flight.google, open up 2 tabs, search for 2 totally different flights. Each tab will show its own flight information. You can go from Bangkok to Phuket, or Bangkok to Japan, or Bangkok to the US, right? To be separate, it's more dynamic. But the bottom line is this: again, our old friend is a file, all right? And who managed the file? Server. Yeah, it's as simple as that. So what's the purpose of Google Chrome? Take the input, display that to you. All right. So Google Chrome, Microsoft Edge, just to make sure it enhances your experience for sure, make it display quickly. Hopefully it doesn't eat your entire memory and then can display all this media for you. Okay. Then the server generates the media for you. There are two types of connections. So now we're going to dive deeper into the 1.0 version and 1.1 version. Now, the first type is what we call non-persistent HTTP. Basically, what it means is I open the connection, send one object, I close the connection. Again, open the connection to do one thing, then close the connection. So that's non-persistent. The reason why we use the word persistent, what does persistent mean? It doesn't, persistent means I stay the same. Non-persistent means it doesn't stay, right? In computer science, you might see this word a lot. In most contexts, if not all, actually, with what I've seen so far, it means the same thing. That's persistent memory, for example, is the memory that I hope when I turn off the computer, it stays there. Persistency is a topic in database as well, right? So in the context of HTTP, you have non-persistent, which is I establish the connection, do one thing, close it. And you have the persistent HTTP, which means that I open the connection to the server, and then I am allowed to do multiple object sending, receiving, before I close the connection. Quick question, which one is better? Persistent HTTP, right? That's why we upgrade to persistent. Well, let's go more of the historical timeline a little bit, right? So here's the example of non-persistent HTTP. I go to mahidol.ac.th, for example. I send the URL over, right? The URL is like www.mahidol.ac.th, right? Hit enter. That URL might, basically the server, when you got that, it might send a bunch of text. And then how many pictures are on the main website in Mahidol University? Like at least 5, right? A few pictures of the university, of the logo and everything. Imagine for every single one of those objects, open connection, send it, close it. So that's the non-persistent HTTP. All right, so you go there, come back, get one object. Just continue of that. Go to the server, right? Go to the server, process it, say, hey, accept, establish connection. Request the message, go to the server again to request the message, process it, send the message back, close it. That's for one image, like the Mahidol University logo, right? And you have to do it for all the websites that you're about to display. Probably not a good idea. Why? There's this thing called RTT, round trip time. What does round trip time mean? Let's say I ask you to, hey, let's go get lunch. You go to the other building, the main building, to go to 7-Eleven and that cafeteria, the big cafeteria area, and come back here. The time it takes for me to go there and come back, that's the round trip time. That's why we call it round trip, back and forth, right? So in this case, yes. Yes. Not, yeah, for non-persistent, it's just open connection, make sure the connection is open, close connection. It doesn't include the time to transmit the file. It's just the time to travel back and forth. All right. Yeah, so the number of objects you have to send over increase the amount of time you have to send and receive the message, right? So for non-persistent HTTP, one single object is 2 round trip time. I need to open and make sure establish connection. So that's the first round trip. Then send a request over. Hey, I want this file. Send it back, close. The closest thing is done, can be done asynchronously on the side, like, hey, I close this, which allow me to open it again. All right. So the response time, again, the response time is the time for me to actually get the file, right? 2 round trip times plus the file transmission time. If you send a small object, it's like so small compared to the round trip time, right? HTTP 1.1, the design in, I think 95, right? 1995, a while back. Maybe that's a good idea to leave the connection open so that you can send multiple objects at the same time, right? I mean, who would have think? But I mean, back in the day, there's a lot more restriction on resource you can use, right? But now computer is fancy, fast, a lot of resource. Server would leave the connection open after sending the response. It's only closed when you need to close. So you can send multiple objects. Open the connection, listen to all the requests, send the data back, and then done. All right. So that's HTTP 1.1. That's the persistent HTTP. Now let's dive a little bit deeper into, we talk about the protocol, right? So what's the message? Now there are 2 types of message, request and response. And as the name suggests, request is when you send a message to something, some entity like a server. I want something. Response is more reactive. I got the request. I will process this and respond back with the reply. All right. So the HTTP request message, thank God, is human readable because it's ASCII. All right. It's not encrypted in binary or something. It's just plain text. Request line start with the command. One example of this command is the get command. So that's the first thing, the command. So you know, okay, this is the request that do what. Followed by the head command, which includes things, it can be including things like the version of HTTP you're using, HTTP 1.1, the target, like index.html. In this case, I want to get index.html. Then afterward, this will likely be important from now onward for your sanity on the project. All right. Followed by backslash or backslash n. For every single line, carrier return line feed /r/n. Okay. That would give you the new line essentially. Then the header comes next. The header always means this. It's like when you send something over, the header is like the first thing you see. That's why we call this header. So the header lines can include things like what's the host name, what is the user agent on the client side, like I'm using Mozilla version 8, for example. And then anything you want to add to actually tell you about the request and the connection. For example, I can keep alive the connection after I send this request, the connection : keep alive, right? Then you can tell that the end of the header line with a blank /r/n. Basically, it's like a new blank line. That would tell the receiver that's the end of my header. The rest is what? The data you want to send. Again, you send a message, right? command, additional information about the command, and here is the data. So that comes next. Okay. Yes. Yep. /r/n, not just /n. Two things. Is the protocol. So one sanity check quickly on your lab if need to. Yeah, that. And here's a more formal definition. It was the same explanation earlier. Method is like get, put, post, like the command, followed by the URL, followed by the version. So that's the first line. Then /r/n. So that's /r is carrier return, /n is line feed. Anyone know actually the historical meaning of this? Anyone seen a typewriter before? How do you enter a new line? That's it. This is called carrier return because that's the carrier to return it. New line feed. So that's why it's /r/n. That's the historical meaning for that. Why do we use it? Anyone wondering why do we use it? Why don't we just go with like /n? What if I built a website back in 1990? It should work, right? So yeah, backward compatibility. Maybe more. I don't know. Like to be honest, I think it's just that. Wait, what? All right. We can keep that discussion after we're done with the recording. Okay. I do have comments. I think I'm siding with you. Again, formal things like well, header field name with the value. In the header, just field name, value, field name, value, field name, value. Why is this nice? Well, anyone use like things like JSON before? Where you have like the key and then the value. It's kind of similar in a sense that you can say, hey, this is a field name for the header. Here's the value, and I can just populate that and say that's it for my header. So there are multiple type of request message. Post, head, get, put. These are some sample of that. Head mean I want to request the head, like send just a request header. I just want to send a header, right? Get means I'm sending data to the server. I'm sending data to the server. This can include things like user data in a URL, right? You use URL before. Sometimes you see something like this question mark thing. Ever wonder what's the question mark thing here? In your URL, like you put in some search, right? And sometimes the link have question mark with the keyword you were just putting in earlier at the end. That's how it embeds the data to the server. Send that message. All right. Put and post are essentially that's something that's similar. That's something that's different. Put means I upload a new object to the server. I upload new object to the server. All right. This would replace any object that exists at the specified URL. So if that URL already, it replaced that. It replaced that. Post means I create a new item, a new object. So if there's something on a server and I put the post method, you basically create a new object. Every time you set a post method, new object, new object, new object, new object. Put, replace whatever is there. Okay? All right. Yes. Get. It's basically here is the data that I want to send to the server. Basically, I'm making the request using the get command with the data I can tag alongside, and I can send that to the server. And the response will start with the status line. Anyone remember like HTTP 404? That's from the response to say, hey, yeah, I 441. Yeah, something not found, right? I put, say, the get command to the index.html is not there. HTTP 404 is not there. All right, so the first line is status line. The server can also then pack the header lines back, right? For example, the server information with the date. Why is the date important? When do you access the server, and when is the file that you're requesting last touched? How many people think that sending file back and forth is a long process? Yeah. So what if I can detect that, hey, that file is the same from the server, and I already have a copy in my machine, right? That means what? I don't have to send the file again. I just display my cache file. Right? In web application, we do a lot of caching. So these are information in the header line that the server can send back to you about the information related to that file. The client will be responsible for that. So, like for example, Google Chrome will manage its own cache, right? So in that case, Google Chrome will have its own algorithm to detect, okay, are we gonna check for every single file? Is it the same as request before? Am I gonna display the cache? Then if it's updated, how do I get the new data? So it's a client application that has to manage it. Yes and no. Yes, yes, that's true. No means they are likely applying almost the same policy. If it's modified, updated. Otherwise, I cache it. Oh, there are multiple ways to do that. Like you can check the last the tag with the MD5, check some or last modified, and a combination of these things. Some of these might also deploy something like, okay, if I haven't accessed this thing for like 500 days, maybe I can throw this away. So the way to clean the cache as well, right? Because if you keep the cache forever, it also means that your computer hard drive is filling up. And here are some status code. 200 is probably the most common. Okay, everything works perfectly. 301 is that object has been moved. Here's the new location. That's an interesting message, right? It's been moved. Here's the new location. 400, that request. Server got, like, it's like the server only understands English and you talk German to the server. Yeah, 400. I don't understand what you're saying. That's the message you get when you maybe pack the request in the wrong way. You forgot like /r, for example, but I don't understand what you're saying. Not found means the document is not on the server. And then 505 means the HTTP version is not supported. For example, you are trying to request version 2 from the server that only support version 1.1. All right. You can try this example. You can use the Telnet program. Go to aboutmyip.com with the port 80. We'll do that. We'll do this during the break. All right. It will give you the HTTP response back to me. You can also do conditional get. This is a more fancy version of get. Right? Instead of just getting the page you want to display on your Chrome, like your client browser, maybe don't send the object if I have this object cache. So that's the conditional get. From the client, I can say if modified since. I can put that into the header and say, hey, if this has been modified since this date, send me that new object because my version I have right now is older than this. In that way, the server can just say, hey, it's up to date You don't have to modify same object. All right. Okay, so that's a pre-lecture. Any question? Huh? Yeah, then we'll talk about the DNS system and how do we actually maintain all this host name without a website you can go without having to remember the IP. All right, so let's do a quick pause here. All right, sorry about that. So let's talk about the DNS system. Okay. The domain name system, right? You think about it, we have the question already from last week, right? That how do we actually maintain out the list of host name and the IP address? Because it's going to be a giant table, right? How many websites are there in the internet? A lot. Okay. The domain name system, if you think about that, right? If you think about it, basically, I mean, I can develop a system that map a name to identifier. For example, I can have a system to develop the connection between your Thai national ID with your name, right? And in this case, I have to build a system that contains how many entries? Like 60 million entries, something like that, like 60, 70 million, right? I can also have the same system to map the IP address to the host name and the domain name, right? How do I map between the IP address and a name and the other way around? I have a name, how do I get the IP address? Because we will, basically everyone right now use this system to connect to the internet. If we lose the DNS, what happened? Every time you go to Google, you have to type the IP address, not the name. Likely not fun. All right. So the way we implement this is we need a distributed database. It's a database where when you have the word distributed, it means it's everywhere. Right? It's different from decentralized, it's totally different meaning. Distributed means I have a database that's spread out everywhere, that are implemented in the hierarchy of many name servers. On the application layer protocol, right? The server communicate to resolve the name. The server, the DNS server, communicate to say, hey, this IP go to that name. This name has this IP and things like that, right? The service is I can have the host name to IP address translation. I can do host aliasing. I can alias the host name to another name for the user. I can have mail server aliasing, and it also performs load distribution. The aliasing basically means that I can have an alternate name that means the same thing. All right, I can have the host name, alias name, canonical name like IBM.com that can actually stand for an actual host name, which is different from www.ibm.com, right? Load distribution means that I can handle the case where some region might search more about certain host name, or not search, my bad, look up more host name on these host name versus another region, right? Anyone watch NFL? Awesome. Only a few people in Thailand, including me. I watched the. I want to use the word football, but I know you guys would know and make jokes on that. It's not football; it's American football. All right. Well, I was in the US for a long time, so I use the word football, which like I like how everyone shake your head. Like over there, we call football soccer to differentiate the two because we don't want to name it American football, right? But how many people would go to NFL.com from Thailand? So the DNS server over here, right, might not have a lot of load, but the load over there in the US is way more. It's like a religion over there. All right. Uh, Load distribution allow the whole service, right, to handle this kind of different in the load, making sure the system doesn't crash. It has a replicated web server, where you have these replicate, like you see earlier, Google, right, correspond to multiple IP. DNS also make sure that a cluster of this server will be like the request to those IP is equally distributed everywhere, right? So that's the in terms of the service side of DNS, if you have multiple IP mapped to like google.com, every server should see the same incoming traffic, not like everything go to the first server and no one see everything else, right? It should equally distribute the load everywhere to all the server mapped to the same host name. Why not centralized DNS? Why do we have this distributed version? Single point of failure, right? If you have a single DNS server and if it failed, your internet failed, right? And it has to handle traffic volume. How many people are using the internet in the modern day where we all have, well, many of us have smartphone, right? A lot. So yeah, you probably cannot scale that well. Just like Comcast is one of the major ISP in the US, right? But think about it, like AIS DNS server, right? We'll have to handle so many queries per day, right? So you have to make sure they scale. And it's basically a humongous database that has billions of records that are super simple, right? IP website, IP website, IP website, but there are billions of them. There are a lot more read than write. How many times you register for a new website as opposed to someone requesting, whereas google.com, right? Read, which is basically, I type in google.com, what's the IP? It's gonna happen way more often than someone register a new website or change my IP mapping. Because those are write requests. Read request means I just want to look it up. All right. It has to physically be also decentralized where it is everywhere in the world, right? And it should be reliable. It should be secure. Like no random person can go in and change the record and reroute Google to some other random IP. It better be secure, right? So as you can see, it's not easy to design. All right. So here's some quick overview, right? You're gonna have the root DNS server, followed by multiple like domain. So you have the top level domain and you have the authoritative domain afterward. The top level domain are like the .com DNS server, which dictate whoever registered that website that ends in the .com, right? .org you have its own DNS server. .edu would have its own DNS server, right? If I go to like www.amazon.com, what would happen is you first go to the root, it will say, okay, go to the .com DNS server. Then the .com DNS server will go to Amazon.com DNS server, which is the next level. Then the client now will go to www.amazon.com. So you have like one step at a time. All right. The root name server is official. This is like contact of last resort. The name server, if I cannot resolve a name, I can always go here. Root name server will have everything. There are 13 logical root name server. There are 13 logical root name server and a bunch of copy of this logical server everywhere in the world. Why do we need this? So that if I am trying to access something from Thailand, I don't have to send the packet over to the US, right? It's going to be annoying. The replication helps in the case of, well, you think about it, geographically caching, right? Geographically, literally as in the geographic, like how we cache one in Thailand so that you can just stay in Thailand and make the whole thing faster. This is incredibly important to internet function. You can't have internet without these things, right? Then ICANN, the Internet Corporation for Assigned Name and Number, it's an entity, it's an organization that manages the root DNS domain. All right. And the top level domain or the TLD, top level domain. These are the servers that's responsible for the .com, .org, .net, .edu, .io, all those .things. Okay. This includes things like .th. These are like top level country domain like .th, .fr for France, .ca for Canada, .jp for Japan, .cn for China. It's a authoritative registry for the like the .com and .net for each of these extensions, if you will, right? edu cost, for example, responsible for the .edu top level domain name server, right? You might also realize for Thai University, we don't register to .edu, right? It goes to .th, which has the next level .ac, right? These are just how each country, if you will, also organize their the TLD and the authoritative server, right? The authoritative DNS server in this case is like just the organization owned DNS server, like Mahidol, right? They provide the host name to the IP mapping for that organization, so it knows the machine inside this organization, like Amazon or Google, and can be maintained. This is basically where the top level hand off the maintenance to the company or the organization, right? So now it's maintained by the organization or some service provider, not this global entity anymore. And you can also have the local DNS name server when I make a query, right? It first go to the local server. It then return the reply. For example, if you go to Disney Plus in Thailand, right? It actually doesn't go to the US version of Disney Plus. It's go to the what? The Disney Plus Hotstar, right? Which is actually a different services. In that case, right, when you are basically going to Disney Plus, there's some rerouting that prevent you to go to the US based version and now maintain it inside the Thai version, right? In this case, right, the ISP, like AIS, what about the ISP now that all this company are merging? That's true, AIS, right? They would have the local DNS server to find the host name that you want to go to and the IP address. Okay. Also, the local DNS server doesn't always have to strictly belong to the hierarchy of this, like top level, like the root, the top level. I mean, there might be like some local DNS server that's not inside this tree. Okay. And you can cache the DNS information because you don't want always to go to the global level. It's annoying in the sense of it's not efficient. Then the local server, for example, can cache the mapping, right? Because how many times Google changed the IP address? Not a lot, right? So you can keep the data in the local server. The TLD server, the top level domain server, for example, is typically cached in your local name server at AIS or True, right? Because it makes sense to just go to that ISP because you have to go there anyway. Your computer is connected to the ISP, right? So they have their own local DNS server, but they can be out of date. So the way we deal with this is we said we'll do best effort. If there's an out of date IP address, I might not know about it until the time expire. There'll be some timer. If it expire, I then request the same name mapping to cache. If it's updated, I'll get it afterward. I'll get it afterward. DNS record will have some of these formats. There are multiple types. There's type A, where I have like the format is name value type TTL. TTL is like how long do I keep it there in the cache? The name for type A is the host name, value is the IP address. For type NS, the name is the domain name, like Amazon.com, Google.com. The value is the host name of the authoritative name server for that host name. What it means is, again, authoritative name server is organized and managed by the organization. So the authoritative name server for Amazon.com is managed inside Amazon. Amazon server handle the lowest level DNS. After you add Amazon.com, Amazon handle the rest, basically. So in this case, the domain like Amazon.com will map to the authoritative server at Amazon headquarters or Amazon's data center that would then reroute your request to the correct server inside Amazon. CNAME is for canonical name or the real name. For example, IBM.com. This actually server is .backup2.ibm.com. So you can make this aliasing, say, hey, if someone go to www.ibm.com, let's say going there, you can make this alias. Type MX is for the mail server, SMTP mail server that associated with a name. Right. So getting your info into the DNS, for example, I can say, hey, I want to register a new website. And let's say I want to register a new website called networkutopia.com, right? The first thing I do is I would then say, okay, I send the NS request type that say, if someone go to networkutopia.com, it has to go to this authoritative server that I manage called dns1.networkutopia.com. Basically, would reroute from the top level domain, right? Allow me to link to my authoritative server for the DNS, inside my networkutopia.com. So that's a NS type. Then you make the mapping and say, hey, dns1.networkutopia.com is actually 212.212.212.1. So that's the A type to then finally map back to the IP address. All right. So in this case, it creates the authoritative server locally at 212.212.212.1 with the name dns1.networkutopia.com. And then if everyone go to, like, say, Google to www.networkutopia.com, then you map to this IP address, which will eventually reroute to the target server that you're trying to service the user. All right. Yes.
Like we did that first time, right?
You mean what type are you talking about? Sorry, I was trying to remember that you have the top level DNS, right? And then you have each organization to maintain their own DNS. So basically that gives you the connection from the top level domain to your own DNS. To like DNS1.network. Your DNS, yeah. 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 Think about it as like I can then hand off the connection to, like, okay, here's just your DNS, manage whatever on your own after this point. Because you can then reroute or remap the IP address, right, if you want to. Yeah. Okay, quick news, P2 is already out. It's on Canvas. Clone the repo. Instruction is super long. Check it out. First milestone is due 7 days from today. Shall we? Let's keep it. Just keep it there for now. Okay, now, assuming that those things is something you watch on YouTube, on the pre-lecture, Ajahn Kanat video, let's actually go to the live session. Live session, which I assume that with no time for this. Please check out GitHub that I have earlier from Ajahn Kanat GitHub that has the demo, because it has a tiny web server that you can play around with. You can run on your machine. Then you go to Chrome, you can then access your own tiny local web server. All right, because the in-class exercise basically asks you to expand the capability from just always sending back hello world, which is not really useful, to do more things. All right. Basically, again, we have the protocol. Protocol define how to communicate. All right. The specification is called RFC 2616, which again, you can go online. There's no point to remember this thing, except when you Google HTTP/1.1 protocol, will give you that. It's as simple as that. Make sure you know it's called HTTP. When you Google, then you search the protocol, it would tell you how to construct the first line, the header, and the body. All right, it will tell you these are the options you can do for the header, and these are what it means. These are what it means for this particular option with this value. These are what it means for this option with this value. If you're from this type of client, this is what happens. For each client, for example, Chrome, Mozilla Firefox, Microsoft Edge, Safari, right? They're gonna basically follow this protocol. And one last thing before we basically kind of wrap things up. This thing just get disconnected. About other battery. All right, so my computer is charging again. HTTP 1.1, as I said, if I use TCP, things are in order. So let's say I request 5 objects. Again, I open the connection, request 5 objects. The first object is 10 megabytes. The other 4 object is 1 kilobyte. What happened? Again, head of line blocking means that the front guy, imagine you go to like a supermarket and then you have to queue up, and if the guy in front of you is like have 5 carts full of something to check out, and you're like trying to check out like candy bars, right? That's head of line blocking. Can happen to HTTP 1.1. The first object want to send 10 megabytes, the other is like 1 kilobytes. That's more like illustration of what happened. Again, I want to get O1, then O2, then O3, then O4. O1 is huge, the rest are small. Everyone has to wait for O1. Bad. All right. This can happen when your first object is like a video file, right? And this can obviously happen in modern day web services. How many of you like have live video on the website, right? Or like a bunch of like huge things to display on a website. So this can definitely happen. HTTP version 2 kind of fixed this by first, I can make the object being sliced up into multiple chunks. And then the client, like Google Chrome, can specify the object priority. It doesn't have to be first come, first serve. And can say, hey, I want to service object 2 and 3 and 4 first, because object 2 and 3 and 4 are small. Then you divide the object into frame. Basically, instead of like a 10 megabytes object, I divide into maybe 1 megabyte frame, so that I service 1 megabyte, 1 megabyte, 1 megabyte, 1 megabyte at a time, and I can cut the service in the middle and service another object. This can hopefully mitigate earlier problem, right? Imagine now if you go to a supermarket, there's the guy in front of you, and you have the magic wand and say, hey, stop whatever you're doing. Now it's my turn. That's it, right? You can also proactively push unrequested objects to the client. What do I mean by this? Let's say I'm on this website and the server knows that every user eventually in the next 1 minute, every user will have to request this object that is like 2 megabytes in size. If my server know that, I mean, does it make sense for me to send it over right now when no one is using it? When no one is using the connection? Yes. That means I can proactively say, hey, let me give you this ahead of time because I know from the sequence of where you're going, you need this. So that when you actually need it, you don't have to load it at the point. You already have it on the client, right? Think caching, right? Caching is a reactive thing. You access the data. And when you access the data is now in the cache. Proactively pushing is like, okay, I know this array is going to access this data, so I push this in the cache ahead of time. Same thing, same concept. All right. So here's how it mitigates the head of line blocking. Again, the object O1, which is huge earlier, now it's breaking down into frame. I can then go, hey, I get O1, let's get O2 the same sequence, get O1, O2, O3, and O4. But now because O1 is in a smaller chunk, I would do the first chunk, then do O2, O3, and then O4. And let's say in this case, O3 doesn't fit in one chunk, right? I'll break them into 2 chunks and do O3 and then O1, O3, O1 until it's done, and the rest are O1. Up on arrival, you notice how you still get O1, then O2, then O3, and then O4 to the client eventually. But in this case, O2, then O4, then O3 arrive first, followed by O1. Okay. HTTP3 is the latest. This version is from June 6th of 2022, which is basically less than a year, almost a year, like 7 more days. It's one year after HTTP is out. These allow you to also kind of use this UDP to transport your data for faster connection, but it's going to be a little bit more error prone, but it allows that. It also adds security at per object error and congestion control. Congestion control is, again, imagine traffic in a network, in a highway in Bangkok. Congestion means there's a lot of traffic on the street. Congestion control is how do I control traffic so that everyone doesn't get stuck in traffic. All right. So HTTP 3 has more option at congestion control. So hopefully every packet is faster. Yes.
What about HTTPS?
HTTPS is the secure version. Are we gonna cover? We can briefly cover that actually. We'll talk about a little bit more about networking apps, and then we'll talk about RPC. I'll try to squeeze in. If it's not possible, I'll think about what to do with module 3 because we can go quickly on caching. We went over that already, so we can dedicate less time to caching and talk a little bit more about HTTPS. All right, yeah. We have a tiny web server as a demo. As you can see, it's 1150. There's no way we can do it here. Please check out the Git repo for the code to the tiny web server because your in-class activity is about that. All right. Now that the exam is over, I do recommend if everyone can watch the pre-lecture video so we can piece out the earlier part and we can do a lot more on the demo and live demo thing. So for example, if on Thursday you can watch the pre-lecture, then we can do this live demo. and then do a little bit Q&A on your activity. We'll spend more time over there. All right. Yeah, that's it for the class today. Again, sorry about my late arrival with the traffic jam. So we'll see you guys on Thursday.